So this is a really quick run through of the new FORCsensei software. This of course isn't the official tutorial, I'll make that once things are done, but this is just to give you a kind of rundown of the new software so that you can provide comments, test it out and so on. So the software is now mounted on a free cloud and typically takes between about 10 to 15 minutes per sample to run. So if you click on the link that I sent you in the email, that'll open up an instance of the software running on Binder. Everything's in a Jupyter notebook, but I've tried to make it as kind of un-notebook-esque as possible, just with buttons to click and so on. So it can take a few minutes to render a new notebook, but here, it took 10 seconds or so, and the notebook will appear. It runs in something called app mode, which means you just see buttons and pictures and things like that, rather than all the code is hidden. For some reason that I'm not sure about, it always takes you to the bottom of the notebook first. So if you just scroll upwards, you can see the top of the notebook, it says welcome to FORCsensei and so on. The first thing we need to do is put some data onto the cloud to analyze. So if you go over to the Jupyter symbol up here and you right click and you say open link in new tab, you'll be able to see in the new tab, these are the files that have been created on the instance in the cloud that's running FORCsensei for you. So you can simply click on upload, and then that'll go to your local disk. You can pull up a FORC file from that, say open, it appears here, and now you can just say upload, and that will load that data file up on to the cloud. Now, because this is just a single cloud instance, if you shut down this web page or shut down your connection to the cloud, that file will disappear. Things aren't stored permanently, but after processing you can download things providing the session is still running. So we can see now our files being uploaded. We can go back to the FORCsensei page, and what we have now is really just working through a selection of tasks for selecting the file, importing, processing, and so on. So I'll go through those one by one just as a demonstration. First thing we need to do is select our data files. We just click on the select button. A little window appears. These are the files that are on the cloud instance. So here's the data file I just uploaded. I can say select. You can see it's now given me the path and name of that file, and I can just click import data. The import is practically instantaneous, and so we can now continue on. We can select our data pre-processing option. So again, we just click this button. That's going to open a menu, should open a menu of different pre-processing options that we're going to perform on the FORC data. Now, I'm not entirely sure. I should have been a bit more patient. It's now opened the thing twice. So I'll just work on this highlighted one. We can, for example, do measurement drift correction. We can do remove first point artifact and so on. We can decide what fields we want to use for removing the paramagnetic slope. We can do mass correction, we can change the sample name and so on, but for the time being I'm just going to do a pretty standard 70% paramagnetic correction, remove the drift and remove the first point artifact. Once I've selected those options, I can just click on pre-process the data, and what you'll see now is these little cogs appear here. That means that the calculation is being performed on the server. The kernel's actually busy, so we need to wait for that. It's disappeared now. The data's been pre-processed. We've got our forks and also our difference curves that we're ready to now perform the analysis on. I should also say this figure has now been saved into the drive. So you can see there's this EPS here, which is the drawing, or sorry, the plot of those hysteresis loops, the fork and the difference magnetizations, and I can simply click on that and hit download if I want to get a local download of it. In fact, I'll do that now. You can see it just goes into my standard downloads as an EPS file. Okay, so going back here, I can now select the different regression model options that I want to run. So what I'm going to do, I'm going to click on this. The menu should appear. You can see there's 3 tabs, one for the models that we're going to run, downsampling, and the number of cores we're going to use for processing. Now, because we're running this on the cloud, I'm going to set this down to 4, and I'm going to start it running. It takes about 10 minutes to run, so while it's running, I'll explain what all the different model options are, but I'll just start that going now so that we don't have to wait for it. So that's going. You can see the kernel's busy again, the little cogs have appeared. So the model ensemble, simple stuff first. We can choose, are we going to work with the magnetizations or are we going to work with the lower branch subtracted data? And then we get into varifork parameters. The code's moved on a lot since the last time people tested it, and the idea now is that you compare a number of different varifork models, and using certain model selection criteria, you choose the one that is most appropriate for your data. And by most appropriate, I mean the one that has the most second-order polynomial surfaces in the individual local regression problems. Smoothing parameters is a little bit complicated, so I'll come back to that. But with the processing, you can decide how many cores you want to run the problem over. This is where it's written in parallel using Dask. On my computer, I'd normally use 8, but on the free cloud, you tend to run into memory problems if you use more than 4. So that's something that we can easily adjust. The downsampling is just to speed things up. When we're testing each varifork model, if you calculate the varifork model for every single data point, it can take a very long time. So what we can do is we can downsample. In this case, we've downsampled to 2,000 data points. What that means is we're going to calculate the fork for our data set at 2,000 different locations through the fork space. We still use the full data set for doing the regression calculations, but we don't calculate the derivative at each position within that data set. We're just calculating the derivative at 2,000 randomly selected positions within the data set. So just to emphasize that again, it is using the full data for the calculation, but it's only calculating the derivative at 2,000 data points rather than the derivative at each data point. Now we get to the model ensemble, which is defining the varifork models that you want to compare. So if you remember, varifork is defined by horizontal smoothing, vertical smoothing, and then a lambda function that says how much your smoothing is going to increase as you move away from the origin. And for example, in the horizontal smoothing, for any given varifork model or configuration, we have to define a minimum horizontal smoothing and a vertical horizontal smoothing. Again, for any given varifork model, we have to consider a minimum vertical smoothing and a maximum vertical smoothing, and lambda is normally a fixed value. So what these sliders are doing is setting up the range of smoothings to be tested. So the horizontal smoothing is only set by a minimum and a maximum. And this slider sets basically the array of different horizontal smoothings that need to be tested. So for example, currently it runs from a minimum of 2 through to a maximum of 8. So that means in the first model, it will consider the minimum varifork smoothing to be 2 and the maximum varifork horizontal smoothing to be 2. Then it will create a model where it considers the minimum horizontal smoothing to be 2 and the maximum horizontal smoothing to be 3. Then it will do 2 and 4 and so on. Then it will start comparing 3 and 3 and 3 and 4. So really what we're doing is setting up a grid of varifork parameters. And this is just defining the limits on that grid. Similarly for the vertical, we're saying that the minimum vertical smooth that can be used both for in any given model, the minimum and the maximum, and then the maximum is 8. Okay, so all we're doing is setting out this grid of potential varifork parameters. Similar with lambda, we're going to test lambda values through all our various smoothing configurations going between 0 and 0.08. So in total, there are 675 varifork models that are currently being compared. And all that happens is, again, this is being performed in parallel. First of all, we'll calculate a varifork model where SC0 equals 2, SC1 equals 2, SU0 equals 2, SU1 equals 2, and lambda equals 0. Then kind of the other extreme in our grid as we work through all these possible combinations would be SC0 equals 8, SC1 equals 8, SU0 equals 8, SU1 equals 8, and lambda equals 0.08. So like I said, we've actually got an array of 675 varifork models across that parameter space. So each model is being calculated separately. That's part of where having the numbers of cores comes in, because we are going to have to calculate 675 different varifork models. And then when we've got them all together, we use model selection criteria to decide which of those varifork models is best. So therefore the assumption is that the best or optimal varifork model is actually contained within this range of parameters. The sliders can be changed, so they go up to a maximum smoothing of 10 in both the horizontal and the vertical, and I think lambda goes up to 0.2. But in most cases you'd say that's probably too extreme. So I've set these as the defaults. They're easy to change, and of course if you pull these sliders out so that you're considering a wider range of parameters, then it just means you have more varifork models to compare and the calculation will take longer. So this seems to be kind of a reasonable balance between range of parameters that you may want to test and the number, or how long we're willing to wait for the calculation to take. Now, another thing that's worth emphasizing is that although this takes about 10 minutes on a free cloud service where we only get allocated 2 CPUs and 1 GB of memory, if we put it onto a private cloud service, then obviously we can speed up the calculation as required by simply paying for more CPU time, paying for more memory, and so on. So we have to kind of make a decision of, is 10 minutes long enough, or people are willing to wait 10 minutes to process, or do we need to offer this in higher speed processing? You can see that the little cogs are still going. But what's going to be output is basically a diagram showing the model selection and indicating what has been selected as the best model, and like I said, that's the one with the most second order surfaces in it, or where the data approximates the most second order surfaces. And it will also provide a plot of where the data is consistent with a first order surface, where the derivative is 0, where it's consistent with a second order surface, and where it's consistent with a third order surface. Once the optimal model has been selected, we can just calculate that across the whole data set, because like I said, at the moment we're downsampling to just 2,000 data points, so we still need to do the calculation for the whole data set, but actually the code's fast enough now that that just takes a couple of seconds. So that isn't a restriction anymore when it comes to calculating the final model. Once we've got that final model, we can plot it. There's an interactive interface where you can add a color scale, you can change the range of the plot, you can specify things like contours, how often you want contours, what thickness you want contours, and so on. Now, of course, all of this can be changed according to what people think works best. The one thing I don't have at the moment that I think would be useful is a way to interactively change the color scaling. So I know that a lot of the work that Shang's been doing recently shows how much information you can pull out on things like hematite components if you're able to change your color scale. At the moment I'm just using the default color scale that's the same one as used in FORCsensei. But like I said, ultimately, if I can create something with sliders in it and so on, so that people are able to play with the color scale and bring out that finer detail, then that's something that would be good to do. A further addition since the previous version is now an ability to plot profiles through the data, and that includes the confidence intervals on the data as well. So people can say, do I want to plot a horizontal profile or a vertical profile? They can then set the limits of that profile. They have to do that using sliders. They can't do it just simply by clicking on the graphic. And once they've got that, then they can finally do the plot, and those profiles will be plotted and available for download and so on. Now, the way that this notebook is structured at the moment is it's still very kind of linear, where you're expected to work from the top and work downwards. There are certain situations where you can go back and change things, and things will be automatically updated. But there's other situations where, for example, if you chose that you were going to change the range of the smoothing or something, you would actually have to process the entire thing again. So I haven't got it yet where you can just flick backwards and forwards in the notebook. It's assumed that things are going to happen in a very specific order. And I guess the recommendation there for people is kind of decide in advance what you're going to do, to process different samples, start different instances on the cloud and so on, rather than simply trying to use one notebook to process everything in one go and so on. Okay, so that's not quite as nice as it could be in terms of usability, but it's difficult, particularly in the parallel processing, to set things up so that you can go back and modify things and everything's updated automatically. Okay, now this is still running. You can see the little cogs are going here. I'm kind of run out of things to say. Maybe just while that's running, I can talk a little bit about how the code is on the cloud. Basically, all the code is on GitHub, and this cloud service, it's called a binder service. This is a free version, but there's other pay for options as well. What they do is, if you have all your code, you have a Jupyter notebook in your GitHub repository, and you include a few configuration files that say things like what packages you depend on and these kind of things, it will automatically build this instance of the notebook on the cloud for you and do all the calculations. So in that way, it's a really convenient way of being able to update things. So all I have to do is update the code on GitHub, and that will then, the next time I launch an instance on the cloud, it will automatically use that instance. So it's very easy to maintain. You barely need to interact with the cloud at all. That's all automatic. And of course, the good thing with this is it means that if everybody's using the cloud, we don't have to worry about people installing specific packages with respect to Python and the various issues that we hit on before, where it seemed that almost everybody had a problem, and each time it was a different problem, and it was quite difficult to try and debug those problems remotely. By putting it onto the cloud, everything has the correct dependencies, everything should run consistently, and we shouldn't have any of those kind of problems. Now, this is still going. I was hoping it would have finished by now. We should be pretty close to it finishing. Obviously, if we tune these parameters up, the thing could run a lot longer, and if you've got a larger data set, it's going to take longer as well. But these free cloud instances are available for 60 minutes while your notebook is active, and 24 hours while your notebook is active. And if there's any inactivity in the notebook, it gets shut down after 60 minutes. So in theory, as long as people are willing to wait, they could process even large data files on this system as well. Okay, so what I'm going to try and do is simply pause the video recording, and I'll just wait until processing is finished. Okay. Okay, we are back, and not surprisingly, it took about an extra 20 seconds after I'd paused the video until it had finished. So what it's done now, it's gone through those 675 different varifork models and it's selected the one that it says is optimal. So these are our selected varifork smoothing parameters. And this is, like I said, trying to find the model where we have the most second order surfaces, so it's not overfitting the data and it's not underfitting the data. So we can actually look at the proportion for any given model, which is the black data points here. We can look at how often it's overfitting, how often it's underfitting, and how many times it's coming up with a second order surface, and we simply come up with the model that has the most second order surfaces in. This is the fork space representing the same thing. So black regions are where we would overfit, blue regions are where it's optimal second order, and the red regions are where we would underfit. Now the reason there's so much black here is because there's so much white space in this, or it's basically the derivative is 0. So what it's identifying here is that actually we should be fitting with a first order model that has no derivative in it rather than fitting a second order model. So now that we've got that model, we can calculate the final model. So that's just using those varifork parameters, and it's now doing it across the entire data set rather than 2000. You can see that just took a couple of seconds. And now we can plot the final model. The plot doesn't actually appear until you change something on the interactive menu. So for example, include color scale, and we now have our final fork plot. And of course you can modify these with the various options here. I've already been talking long enough. I'm not going to do that. You can play around with that. And if I wanted to, I could configure fork profiles. So I can say, do I want to plot a horizontal profile or do I want a vertical profile? If I'm doing a horizontal profile, in this case I'm going to set it through to on the vertical axis is equal to 0, and I'm going to plot across the whole range of HC. I could, for example, pull that in if I wanted to and change that to a given value. I can also click here and change it to a given value if I want to as well. Okay. And then once I've made my selection, I can just say plot the fork profiles, and the profile appears there with the uncertainty on the derivative. All of that's been saved, all of these have been saved into the drive on the cloud and can be clicked and downloaded. So basically that's it. Again, if you wanted to now process a different fork file, the idea would be that you start a new instance on the cloud rather than going all the way to the top and restarting everything. But let me know what you think, send me any questions, any bugs you find, and so on.